computer. All right. All right, let's get started. Are you able to see the slide? All right,
Yeah, we can.
wonderful. Okay, probability, something really dreaded to a lot of people. Uh, to some people, it's fun. I belong to the latter category. I always belong to that latter category. But I must admit that
Rishi, your voice is mild. Is it only for me or for everybody? Usually your voice is much more louder.
Excuse me. Audio is low.
wait, let me just see.
Recording in progress.
Is it still mild?
This is better, Rishi. Yeah.
All right. So if I go mild, please do tell me. All right. Okay. Uh, Let me just see if there's any other setting that I'm supposed to fix. I think it looks okay unless internet is bad, but I don't think that's the case. But just keep me informed, okay? If I'm not audible, keep me informed. All right. So probability, as I said, dreaded to some, fun to others. I fortunately belong to the latter category, but I must admit, I learned probability the wrong way. Uh, and it goes back to how, when we discuss linear algebra, I said something that let's not be caught in the tyranny of geometry. Geometry is deceiving. It will lull you into thinking that you've understood linear algebra, and the moment you transition from 2 dimensions to n dimensions, you will find that your understanding is limited. Probability does something very, very similar. And one of the reasons why you get caught into thinking that you understand probability is because of 2 kinds of problems we face in the world of probability. One is the coin problem, and the other is the dice problem. So any probability paper from class 11, 12, I'm pretty sure there's no paper which doesn't have the coin problem, and there's no paper that has the dice problem. And to solve some of these problems, you don't need to have an in-depth understanding of probability. Some intuition as to how a coin, I mean, the outcomes of a coin, the outcomes of a die is more than sufficient for you to solve. So at the end, you might end up solving the problem, but your understanding of probability could be very limited. And you will find that when you take complex problems, your understanding is, it falls short of what is expected. So my argument is don't rely on class 11 intuition, learn the rules, which is why I say let's learn probability the axiomatic way. Basically, a bunch of rules that we need to understand and apply those rules. The coin problem and the die problem is useful to understand the intuition behind the axioms. And that's why it stops. Beyond those toy problems, as they call the toy problems, by the way. The coin problem is considered to be a toy problem. The dice problems are considered to be a toy problem. Beyond them, intuition is not going to help. The rules are going to help you. So it's very important that you understand the rules. All right. So start thinking axiomatically. Now the question is, what are the axioms? But before that, let's look at the toy problem, the standard set of toy problems. A 6-faced die is rolled twice. what is the probability of getting 1, 1? A 6-face die is rolled twice. What is the probability of getting 1, 1? Anyone on the call? Not the usual suspects. I don't want Abhinav to answer, but someone else for a change. I know, Abhinav, you're not liking it, but still, I can see that on your face, but still. Good.
Is
All
it
this
1 by
is
36 VC?
all right. Who was that?
This is ministry.
All right. Okay. Yes, it is 1 by 36. I know there are some people talking behind the scenes, but that's okay. Ministry. Why 1 by 36?
Since we are rolling the dice twice, it will be like 6 into 6, 36.
Mm-hmm.
And while rolling the dice, there is only probability of getting 1 and 1. It's like there's only one chance of getting 1.
All right. Okay. Anyone else?
It's
Anyone
because there
else?
are 36 possible combinations that can
Okay.
happen, right? So, and there is only one possible way that die should show 1, 1. So,
All right. Okay. Anyone else? Let me put it this way. The answer is right, but can someone give me another explanation?
We see, I'm saying that it has to be rolled twice.
Mm-hmm.
So first time I roll, my chance is 1 by 6. The second time I roll, the chance is 1 by 6. So then I multiply those two. From there, I get 1 by 36.
Okay. All right. I've got 3 answers so far. All 3 suffer from the class 11 problem that I said. None of them. Arun jumped the gun. Arun directly went to what is called as independence of events. All right. He like jumped 3 steps ahead. He is right. I'm not saying he's wrong. He's right, but he jumped 3 steps. Ministry was right, so was Pavitra. But the reasoning was incorrect. All right. Though their answer is right. There were a lot of assumptions in their reasoning, but they didn't tell me what the assumptions were. Okay. But that's fine. No problem. We know that this is how we approach probability. Let's take the second problem. A coin is tossed 5 times. Okay. A coin is tossed 5 times. What is the probability that we will get exactly 1 head? Okay, I don't even want the answers. Just someone tell me the approach. That's a free shit. I'm not seeking answers here. Anybody can do multiplication and get an answer, right? Or division to get me an answer. I don't want answers here. Anyone? Feel free, folks. I know I'm not particularly kind, but still feel free. I'll ask a lot of questions maybe, but feel free. Give it a shot, folks. Come on. There are 26 on this call, excluding me. You understood the question?
We see if we are tossing 5 times means for the first time we have 2 possibilities,
Mm-hmm.
and after that, if we choose one, I mean, so
So the
so
question is
next
simple.
time
I
we'll be
I
having
toss the coin 5 times. The question is, what is the probability that we exactly get 1 head?
You see 5 into
a continue.
1 to the
Yeah,
half
go
to
ahead.
the power 5.
Yeah, 5 into?
Half to the power 5 is in case 4. 4
Okay,
are
half to the
16
power
into
5. All right, but tell me the logic.
Mm, okay, we are tossing 5 times. In 5, we need 1 head, so 5C1. So, which
No,
in
you're
case we
jumping.
need one
You're jumping
success
the gun.
in.
You're jumping the gun. You're already moving to
Okay,
binomial
I know.
distributions, right? But
Sorry.
without that, tell me.
But that's actually that's the way it should work, I thought. I don't think.
No, that's
No,
okay. Easier way to put it is, can we say the
Okay,
first toss can be
in
head
one.
and the rest
Okay,
4 can be tails, correct?
so there are five such combinations. Where in one case it can be second, in one case it can be third. So five such events could occur, or which by R condition. So R in the sense we are adding up that five events, so we get five. But the output of the event is one success, which is 1/2 power 1, and four failures, which in case four tails. So 1/2 to the power 4, so half to the power 5.
Okay,
So adding up, we get
okay, your answer is right. Your approach is close to axiomatic, but
this is okay.
sorry, go ahead,
Yeah.
Arun.
So what I think is like, first of all, I'll try to find out the outcomes. What are the possible outcomes? So that comes as my set, full set, and from that I say like, then I know like which is the. Then you are actually giving me a. I would say like this one, right? You have to select something from that particular set. So then I'll say like, okay, select it. So that is if it is actually a combination of one by something, or the set consists of two by the something means that the whole set. So we are actually trying to probabilities like that. Maybe we call that as a population. There is a population, and then trying to get a sample out of that. And what is that? If I just take that, how many samples is actually possible, fulfilling the criteria for which I'm actually selecting that one. That becomes my new set, and over the full population set is there. The probability is nothing but whatever they have actually selected based on the condition by the total.
Yours is definitely in the axiomatic direction, but you've still lost the plot. I'll tell you why. Okay, let's go back to the. Yeah, sorry.
Can we use binomial distribution?
And again, you guys are all jumping the gun. That's
Yes,
what.
I wanted to give a try, you see.
Go ahead. Yeah, your
Yeah,
answer
it
is
is
right,
like,
by the way. Abhinav, your answer was right. Okay.
so it is tossing, a coin is tossed 5 times. Okay. So I'm tossing it. First time I get a head, remaining is tail. So I've stopped once I got the head. So similarly, this head, right, it can occur anytime. So first time if I'm not getting a head, second time I'm getting a head, remaining
Correct.
is. Similarly, you go for a third time also, right? First 2 times you are getting a tail, third time you are getting a head.
Correct.
So you need to get all this combination.
Correct.
And at the top is probabilities to it's over getting one head over the number of combination of this.
Correct. You're right again. Okay, let me put it this way. Abhinav came closest when it comes to the axiomatic way of tackling this problem. Okay. I'll tell you why a little, in a short while. There is one thing that none of us thought about, which is, I just said a coin is tossed 5 times. I never told it's a fair coin, number one. Nobody even thought about it. All right. So there, your argument fails. Some of the arguments fail. I'll give a better example here. Take the 6-face die. You roll it twice. Now, in all our arguments, we very comfortably say 1, 1 can occur once. And there are 36 outcomes. So 1/36, right? That's the usual answer that we give. But what is the implicit assumption there? The implicit assumption is 1, 1, 2, 2, 3, 3. Each of those combinations have equal probability of occurring. That's the implicit assumption, right? If that assumption breaks, then the answer that Ministry gave or Pavitra gave, which was 1/36, that answer breaks too. What happens if this die is a loaded die? What do we do then? What if the probability of getting 1 is not 1/6, but let us say it is say 2/6, for instance, 1/3. It's a very loaded die, let's say, skewed towards 1. How do you tackle that problem? Now, what typically happens is the moment we are faced with the problem that I said, you will get confused because You solved the basic toy problem, not axiomatically. The way you solved it was, it's just intuition, right? 1, 1, there's only one time it can happen. 36 different possibilities. So I'll take 1 in the numerator, divide 36 in the denominator, and that's my answer. So what I would suggest is, whenever you face a problem in probability, do not jump the gun. Number 1, all right? Try to solve it axiomatic. And the question is, what? I've been using this word, axiomatic. What the hell is axiomatic? Which is what we're going to come to now, all right? And we'll revisit these problems a little later, maybe not today, where we'll try to solve these problems axiomatically and see what answer we get, all right? Of course, we'll get the same answer, but the approach will be very different, okay? So let's see, what is this axiomatic approach is all about. So the first things first, key terminology. This has to be registered right into, right in your head. It's extremely important. There is something called as an experiment. It could be toss of 1 coin. It could be toss of 10 coins. Each of them is an experiment. So 1 toss of a fair coin is an experiment, all right? Then you have the sample space. The sample space, basically, think of that as a set. I hope all of us remember set theory, right? What you have in the sample space is a set of all possible outcomes, okay? So if you toss a coin, it's head or tail. These are the 2 outcomes, right? Let's say I toss a coin twice. Someone, what are the outcomes? Anyone? Simple, right? I toss a coin twice. What are the outcomes? Come on, folks. Simple. I just asked for the outcomes. No, Abhinav, no. I know you'll answer.
Head,
Come on.
tail, tail,
Head,
tail,
head,
tail, head, head.
tail.
All right. Okay.
Head, tail, tail, head.
Okay, good. So you have, how many outcomes are there? 4 outcomes, correct? Have I even talked about the probability of these outcomes? No, I haven't. All right. Okay. Then we have something called as an event. An event is a subset of the sample space. Okay. Be very clear. An event is a subset of the sample space. So for example, in this case, this is an event which is defined as the occurrence of head is an event. Can somebody tell me, if I define the event as occurrence of a head or a tail, what would that subset look like? The event subset. Anyone? Occurrence of a head or a tail. Let's say that's how I define my event.
There'll be 2 values, THHT.
No. Be careful. I'm
Okay, sorry, there'll be 3 values.
I'm tossing the coin just once. Abhinav, no, wait. If nobody answers, you answer, okay? I toss the coin just once. I have a sample space. The event is a subset of the sample space. Remember that, folks. It doesn't come out of thin air. It is always a subset of the sample space. Here is a sample space. And the even that I'm defining is the outcome is a head or a tail. What is the event now? E is equal to anyone? Yash, anyone?
H, T.
Correct. H, T. Evident, right? Next question. I define the event as the occurrence of neither head nor tail. I define the event as the occurrence of neither head nor tail. What is a subset? What is the event?
It's an empty sum.
Empty, because of course, there's nothing like that in the sample space, right? Okay, very good. So you have an experiment. The experiment generates this sample space. From the sample space, you can define event. Question, can I have more than one event defined on the sample space? Not the usual suspect, someone else, not Yash, of course not Abhinav, but someone else. The question is, can I have more than one event defined on a sample space?
No, you see, because it's a subset.
Why not? Let me give an example. Tell me, okay? Here's a sample space. I define an event as if I toss a coin and then a head turns up. That's an event. I can define another event. I toss a coin, a tail turns up. That's another event, isn't it? I define the third event. I toss a coin, I get either a head or a tail. That's the third event, isn't it? Fourth event, I toss a coin and neither head turns up nor tail turns up. That's another event, correct? So haven't I defined 4 events based on this simple sample space h comma t? Haven't I?
Yeah.
Right? So you can define a lot of events on the sample space. So let's be very, very clear. Experiment. An experiment generates a sample space, which is an experiment will result in outcomes, folks. That's extremely important to understand. Okay. So you need to know what the outcomes are, and they're very, very defined. And then you have the sample space. All right. The outcomes, the set of all outcomes is your sample space. Then you define event or events for that matter, which is a subset of the sample space. And finally, you have what is called as a probability function. The probability function basically maps a number between 0 to 1 to each outcome in the sample space. So there are outcomes in the sample space. What the probability function does is, here are 2 outcomes, H and T, right? So for each outcome, the probability function defines a probability. Let's put that as a number between 0 and 1. All right. And it, as a function, it maps the outcome. So if you look at this, right, in the bracket, what do you have? You have the outcome. So when you say probability function, remember, folks, whenever you use the word function, if you remember f of x, x is the input, correct? In the probability function, what is the input? The outcome is the input. And what do you get? You get a number as the output. It's as simple as that. So if you have 2 outcomes here, what do you get to see here? In the probability function, I'm defining 2 values. When the outcome is h, the probability of h is 0.5. When the outcome is tail, the probability of tail is 0.5. All right. Of course, it's not necessary that it has to be 0.5. It could be something else as well. Now we'll come to that a little later. All right. But that's your probability function. So an experiment results in outcomes. You define all the outcomes and put that into what is called as a sample space. An event is a subset of the sample space, and the probability function maps the outcomes to a number between 0 and 1. That's what a probability function does. Any questions so far? Because the next step, we're going to clearly define what a probability is. And you'll be surprised, it's none of the conventional definitions that you know. Any questions so far? All right, okay. So here we go. So we're going to define probability function with a lot of care, okay? Just look at the left part. What do you mean by discrete sample space? S. So by the way, folks, sample space, it's either omega or S. Both are conventionally used, okay? Now, what do we mean by discrete sample space? Anyone? So when we toss the coin, is it a discrete sample space?
Yeah, because
Yes.
Why is it discrete?
it is countable.
Exactly. So if the sample space is countable, it's called discrete, folks. Okay. Does that mean the sample space? I mean, could you generate a sample space that is not countable? Yes, it is possible. All right. That's when we deal with continuous functions, but let's not worry about continuous for the time being. Let's just focus on the discrete bit. Okay. So for a discrete sample space S, a probability function assigns to each outcome W. Imagine W to be an outcome. All right. So in the case of the coin toss, there were two outcomes. So imagine a W1 as H, W2 as tails. All right. So a probability function assigns to each outcome W a number called P of W, which is a probability of W. P should satisfy two rules. That's it. Rule number one, P of W should be between, not be, inclusive 0 and 1. It should be between 0 and 1. Okay. So probabilities are between 0 and 1. Both 0 and 1 are inclusive. And rule number two, the sum of the probabilities of all possible outcomes should be 1. That's it, folks. Nothing else. These are the two fundamental axiomatic rules of probability. All right. So, which means, let's go back to, give me a moment. Why is my screen stuck? All right, go to the key terminology. Here's your sample space. Imagine this to be W1. Imagine this to be W2, two outcomes. What does the probability function do? There are basically two rules. Rule number one, the probability of an outcome has to be between 0 and 1, number one. And the sum of probabilities of all outcomes should be equal to 1. Can somebody tell me why should it be equal to 1? Why should the sum of all, I mean, if you have outcomes of an experiment and you have a probability function, P of W, why is it that the probability of, I mean, the sum of probabilities of all outcomes should be equal to 1? Why?
Because the values that are listed as set is only can happen.
Exactly. So one of them has to happen, isn't it? Correct. So, for example, if it's head or tail, either head should occur or tail should occur, right? So something has to occur. So you can't have, so when we say, for example, let me put it this way. If I ask a question, what is the probability of head occurring or tail occurring? I'm using the word or. Can somebody tell me what's the probability of head occurring or tail occurring? 1, correct? Why did you say it's 1? Did you go by the 0.5, 0.5?
No, VC.
Okay. Why did you say it's 1?
Anyway, anyone should definitely happen. So there is no other
Exactly,
option.
because my sample space, there are only two outcomes in the sample space. If I frame the question as either this occurs or that occurs, then one of them has to occur, isn't it? Which is why the probability of head occurring or tail occurring will be equal to 1, right? Now, if you look at this, I'll repeat this again. For discrete sample space S, a probability function P assigns to each outcome W a number P of W called the probability of W. P must satisfy two rules. Number one, it should be between 0 and 1. And the sum of the probabilities of all possible outcomes should be equal to 1. All right. Now, these are the rules. Now, remember what I talked about, when I said events. What is an event? An event is a subset, correct? So, for example, one subset could be H, and T itself could be a subset, isn't it? Or H can be a subset, or T can be a subset, right? Okay, let me ask a question. I'll just open an Excel so that you understand. I'll pose a little difficult question. So let's say I roll a die, and let's say probability of 1 is equal to, say, 0.2, probability of 2 is equal to, say, 0.3, probability of 3 is equal to 0.1, probability of 4 is equal to again 0.1, probability of 5 is equal to 0.2. Can you tell me, okay, before I proceed, when I roll a die once, what's the experiment? Rolling the die once is the experiment. Can somebody tell me what are the outcomes? Anyone?
Each will be 1/6.
No, I didn't ask. No. What are the outcomes?
1, 1,2 up to 6.
Sorry, say that again.
1,2 up to 6. Like 1, 2, 3.
1, 2, 3, 4, 5, 6. Those are the outcomes, right? So going back, the sample space is this. All right. Now, and what did we say? What is the probability function? We said the probability function is to each outcome, we define something called as a P of W, which is between 0 and 1, right? That's what a probability function is. And the second rule suggests that the sum of all probability should be equal to 1, correct? Now, can you tell me, I haven't defined P of 6. I've defined P of 1, P of 2, P of 3, 4, 5. Now, let us say I define P of 6 as 0.4. Is this a probability function?
No, it's not.
Why?
Because it's not summing up to 1, right?
Okay, so it's because it's failing rule number 2,
yeah.
Isn't it? Correct?
Yeah.
So essentially, for something to be a probability function, it has to satisfy both rules. Rule number 1 and rule number 2. Okay. So now let's say, now tell me whether, let's say this is, give me a moment. 2.3. Okay. Now, wonderful. The sum is 1. Is this a probability function?
No, we are
Why?
overruling rule 1.
Exactly. Why? Because of two things. One, I see a negative number, not acceptable. I see a 1.2, which is greater than 1. Again, not acceptable, right? So, can somebody tell me, I've defined all this, all those numbers look good. What should be P of 6?
0.1.
0.1, right? That's the only thing which will make this sum 1, all right? Now, now I'm defining an event. The event is defined as the occurrence of odd number, all right? Now, can somebody tell me what is E? It's a subset, right?
1, 3, 5.
Okay, 1, 3, 5. Question. Are outcomes disjoint? Are outcomes, so these are the outcomes. Are outcomes disjoint? You understand what disjoint means? Goes to set theory. Occurrence of one precludes the occurrence of another, which means if something occurs, the others cannot occur. My question is, are outcomes disjoint?
Yes.
Are they always disjoint?
If it is a fair die, yes.
Why? How does fairness matter? How does fairness matter when it comes to figuring out whether outcomes are disjoint or not?
No.
It doesn't matter, right? Yash. Where are we talking of probabilities? When we talk of disjointness, did I even use the word probability function? We haven't gone to probability function yet. My question is, I've rolled a die. There are 6 outcomes. Are they disjoint or not? Does the occurrence of one of these outcomes preclude the occurrence of the others?
It does not.
Yeah. So which means, are they disjoint? What does that mean?
Yes.
Yes or no? Yes.
Yes,
All right.
yes.
All right. Okay. So outcomes are disjoint. You take any experiment, folks, any experiment in the world that you can conceive of, and you come up with outcomes, all outcomes will be disjoint, period. Tomorrow it will rain or not rain. 2 outcomes. Are they disjoint? Folks?
Yes.
Yes or no? Yes. Right? Tomorrow it may rain. It may not rain. It could be sunny too. Are the outcomes disjoint? Anyone? Rain, not rain, sunny. Are the outcomes disjoint?
No.
Why?
Because not rain and sunny can occur at the same time.
You're reading too much into the English, right? I just said there are 3 outcomes. All right. You're reading too much, but yes, I get what you mean, but just don't read too much into the English. But assuming that there's a rain, not rain, and then sunny. Okay. But okay, maybe I gave a bad example. Rain, sunny, dew. Okay. They don't go together. So the 3 are very different outcomes, right? So see, the point that I'm making is very simple, folks. In an experiment, if you think of outcomes, and if you find that they're not disjoint, then they're not outcomes at all. You got the wrong outcomes. Let's make it very, very clear. So for example, if I toss a coin twice, all right? We all know head, 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 tail, tail, head, tail, tail. We all know this. 4 outcomes, correct? Are they disjoint? Are they disjoint? Anyone?
Yes.
Yes. If I get a head, head, I cannot get a head, tail, or a tail, head, or a tail, tail, correct? Sometimes you might get confused between these 2. Are they disjoint?
Yes, they are different. Yeah, they are.
They're different. Why? Because in the first case, the first toss is the head, the second is the tail. Here it is the first toss is tail and the second one is head, right? So they are disjoint. So always remember, folks, when you come up with a sample space for a probabilistic experiment, outcomes have to be disjoint. Okay. If you find that they're not disjoint, you got the outcomes wrong. As simple as that. Okay. Now, when outcomes are disjoint, so let's say I define this as W1, W2, W3, and W4. All right. Don't you see one of them has to occur? Would anybody disagree with me? One of these outcomes has to occur. Are we clear? Why? Because there are 4 outcomes. There are only 4 possible outcomes. So we expect one of them to occur, right? Now, I define P of W1 as the probability function here. P of W2, sorry. P of W3 and P of W4. All right. For 4 outcomes, I've defined a nice probability function. A probability function is defined on each outcome, folks. Be very clear about it. Okay. For each outcome, you have a probability function. It's the same function though. All right. But not the same function. You have a function. Let me put it that way. Okay. I don't want to use the word same function here. Now, of course, there's some value. P of W1 is something, P of W2 is something, W3 is something, W4 is something. Now, the question here is, since they're all disjoint, which means if one occurs, the other cannot occur. What will be the sum of all this?
1.
1. That's right. Again, goes back to rule number 2. If you go to this, rule number 2 says the sum of probabilities of all possible outcomes is 1. Correct? Now, let me ask a question. I'm going to change the, let's say I define an event as first toss is head. Okay? Can somebody tell me what are the outcomes that shall be part of this event?
Head, tail.
Head. So how many outcomes then? 2,
2.
correct? All right. Now my question is, I have a probability function. I'm not giving you the numbers. I'm just calling this PW1, PW2, PW3, P of W4. All right. I'm asking a question. What is probability of E? Sorry. Probability of something there. Okay, let me put it this way. I don't know why. Don't worry too much, folks. I think something is wrong with. Let me see if. I don't know why it's converting into.
Is it 0.5?
Okay, I'll come to you. Wait, this is where I think. I'll just say probability of event is equal to E. Okay, I'll make it that way. Okay, so Sanjay says it's 0.5. Anyone else? He says probability of 0.5. Okay, someone else. That's Pavitra too. Anyone else? Abhinav, I'll wait for
It's
you.
0.5.
Okay, who is that? Ministry, is it?
Yes.
All right. Okay. Anyone else?
P of W1 plus P of W2.
Okay, good. That's the answer. It's not 0.5, folks. It's P of W1 plus P of W2. Kyle, why?
Because we have not assumed it as fair coins.
Exactly. I never told anyone here that it's a fair coin. What we have is I've clearly defined a function P of W1. I have a P of W2, I have a P of W3, I have a P of W4. So I have a probability function. Remember, a probability function only maps an outcome, which is W1, which is actually HH, by the way, all right, to a number. That is all that it does. I never told you that this is 0.25. Did I tell you? I didn't. I didn't tell you that this is 0.25, this is 0.25, this is 0.25. I never said any of those, right? So which means assuming that it's fair, unless I've told you, is not fair at all, right? So evidently, when I'm calculating probability of the event E, I know the event E comprises of 2 outcomes, W1 and W2. And are these disjoint? Yes, they are. Why? Kyle, why are they disjoint? Are W1 and W2?
Because both.
Go ahead.
They cannot occur at the same time.
Exactly. Exactly.
Yeah.
2 things can't occur at the same time. When 2 things, so as I said, you take any outcome, folks. You take a bunch of outcomes, none of them can occur at the same time. Only one of them can occur, right? So when I have event E, which is a combination of outcomes, the probability of event E is simply the sum of the probabilities. That's it. Nothing more, nothing less. If I define event E as, say, first toss can be head or tail, second toss can be head or tail, correct? Let's say. Now, can you tell me what are the outcomes that will be part of event E? What are the outcomes?
All four.
All four, correct? So the probability of event E would be P of W1 plus P of W2 plus P of W3 plus P of W4, correct? We know that this summation is equal to 1. We know that, which is why the answer would be 1. Though axiomatically, the probability is merely P of W1 plus P of W2 plus P of W3 plus P of W4. That's how you're supposed to look at it. But it just so turns out that the summation is 1, and which is why the answer is 1. Now, going back to this problem, this event E, occurrence of an odd number. So everybody said it's 135. My next question would be, what is P of, sorry, again, I don't know what's wrong with the event is equal to E. It's technically P of E, folks, but whatever, all right? So what's the probability of
0.5
who was that?
separation.
Okay, why?
So I'm taking sum of P of 1, P of 3, and P of 5.
Okay, why did you take the sum?
Because it's an independent event, right?
Oh, look, very careful, folks. Very, very careful. You're using the wrong term there. It means it gives a very different complexion to the question. Are they independent?
Because they are disjoint.
They are disjoint.
Yeah, it is disjoint, not independent.
Independent means entirely something else. Never ever use that word. All right? In this context. The two words that you can use is...
Sorry to interrupt you, but I also first thought, like before introducing the word disjoint, I also thought the term independent. What's the
Independent
difference
means...
between...
We'll come to that. We'll specially define what exactly independence is, but that comes later. Okay? The operative, you can use two words here, disjoint or mutually exclusive. Both are equivalent here. Remember, folks, an outcome of the experiment, you have a bunch of outcomes of an experiment. They are not independent. They are mutually exclusive. They are disjoint. Why? Because the occurrence of one precludes the occurrence of another. Independence means something else. We'll define it very, very clearly a little later. Okay? So, and we know when they are mutually exclusive or disjoint, both of them means the same thing, we can sum the probabilities, right? Which we did here, isn't it? We just summed up P of W1 and P of W2 because we knew W1 and W2 are disjoint. Then you can sum it up, no problems at all. So now, Sabari, can you argue why your answer is 0.5? I want a proper argument now.
Yes, easy. Since it is disjoint, then we can take sum of occurrence of odd number.
Correct. Which
is like a P of 1 plus P of 3 plus P of 5, which is 0.5.
All right. Okay. That's right. It's 0.5. Now, next question. I define an event E1 as multiple of 3. Okay. What's probability of E1? First things, what's E1? Define the outcome of E1.
6.
Okay, 3,6. All right. Okay. What is the probability of E1?
0.2.
Okay, again, argument. I know you can give answers. Give me an argument. Anyone?
So again, these both are disjoint.
Exactly.
So you add the probability of P of 3 and P of 6.
Exactly. Again, outcomes are always disjoint. An event is a collection of outcomes. And we know outcomes are disjoint by design, isn't it? Outcomes are, always remember, folks, outcomes are disjoint by design. So I can just sum up the probability. So Yash was right. So you just sum up the probability of E and probability of 6. So that's 0.2. Okay. Now I'm going to ask another question. Probability of E1 and E2. Okay, before that, I'm defining a new event. I'm calling E3, defined as E1 and E2 occurring at the same time. You understood? I'm completely defining a new event out of thin air. I have, sorry, not E1. I'm calling this, let's say, okay, E, right? Sorry. There's no E2. Let's say E and E1. Sorry. E and E1. I'll call this E2. Okay. I have an event E. I have an event E1. Now I've defined the event E2 as E and E1 occurring at the same time. Now help me with the outcomes of E2. Remember what I'm asking. Okay. I'm asking outcomes of the event E2. Okay. Outcome. So which means you'll have to go to the, the outcome superset. I mean, the set that you have, all outcomes, and pick and choose the E2 ones. Anyone. Not the usual suspect. Someone else, folks. I want to hear from someone else. Who was that? Who was that?
Sirisha.
Okay. Yeah, you're right. 3. All right. So
Mm.
E2 is 3. Now what is, remember, E2 is an outcome. E2 is an outcome. So what is the probability of E2?
0.1.
0. Because we know that 3, all right, 0.1. That is right. Okay. Now I'm going to ask another question. It's a bit complicated, but think about it. Okay. E3 defined as E1, E occurring or E1 occurring. All right.
Mm.
Either E occurs or E1 occurs. Either or. And I define E3 as another event. Now, what is E3?
1356.
1, 3, 5. Who was that?
Yes.
Yes. Okay. So you say 1, 3, 5, 6. What's your argument?
So all the outcomes in E or E1 merged. Is E3.
All right. Yeah, because either this can occur or that can occur. So basically you are merging both of them. All right. So what is probability of E3?
0.6.
How did you calculate that?
I took the probability of 1356
And then
summed
it up. Correct. Okay. All right. So now there is a simple rule that helps us to get to this number using this, this, and this. Do you know what it is? You know what is this called?
Yeah.
In set theory world, what is this called?
This
E
is
occurring
union.
Intersection.
Union. This is union.
Union.
This is union. The other previous one was intersection.
Intersection. So you remember, folks, A union B is equal to A plus B minus what?
A intersection.
A intersection B.
Correct. A. I'll just call it intersection B. Correct. So you can basically apply the same thing to probability. So you have A union B, which is set here, which is a set E3. Correct. A is say E1. You know the probability is already 0.5. Okay, you have that. So probability of E. So I'm calling it event E because 0.5. Probability of E1 is 0.2. All right. And then E intersection E1, you know that probability is 0.1. You already figured that out, correct? So which means you can say this is a union, which is E3. Probability of E3 is equal to Probability of E1, probability of E plus E1 minus E intersection E1. So which is nothing but 0.5 plus 0.2 minus 0.1. All right. This is very basic law. Okay. So the idea is simple, folks. Work with outcomes. Start with outcomes. A collection of outcomes will give you events. And always remember, from outcomes, when you go to events, you can comfortably sum the probabilities of the outcomes to get the probability of the event. Why? Why? I'll repeat again. When you move from outcomes to an event, you can sum the probabilities of the outcomes to get to the probability of an event. Why?
Because calculating the probability of outcomes is easy.
No. I need a better answer. Axiomatically, why?
Because they are disjoint.
Exactly. That's it. From outcomes, when you go to event, you know that any event, folks, when you explain an event in terms of the outcomes, we know that the outcomes are disjoint, correct? So the probability of an event will be the sum of the probability of the outcomes. There's no other way you can calculate probabilities, isn't it? Is that clear? Because when you define an event, see, remember, this became complex because we defined E3 as the union of E and, was it E and E1? Okay, let me put it this way. We define E3 as union of E and E1. When I define it as union of E and E1, I haven't defined it as, I haven't defined it as outcomes yet, right? I have an E, I have an E1. I said it's a union of E and E1. But if I clearly say E3 has the following outcomes 1, 3, 5, and 1, 3, 5, and 6. It's very clear, crystal clear. E3 is a combination of these outcomes. So which means the probability of E3 will be the sum of the probabilities of the outcomes. No question at all. But here, I was playing some tricks here. What was I doing? I didn't define E3 as a set of outcomes, but instead I chose to define E3 as a set of events itself, a union of events. When you do that, then all this hanky-panky stuff, figuring out whether it's union, intersection, all that will come into picture. But fundamentally, as long as you go to outcomes, it merely sums up, nothing more. All right. So when you look at this, look at this. The probability of an event E is a sum of probabilities of all the outcomes in E. That is, P of E is equal to sigma P of W, where W belongs to E. Now, can somebody explain what this expression means?
The probability of an event.
No, you're not particularly audible, Yash. Your voice was breaking a little bit. Okay, someone else. If Yash is not audible, someone else.
The probability of an event is the summation of all possible outcomes.
That is right. But what does W belongs to E means?
W should be the subset of
the outcome subset of the event.
Sorry, say that again.
The outcome is the subset of the event.
Outcomes.
It belongs to the event, the outcome.
Okay. Is outcomes a subset of the event or?
Disjoint.
Now, outcomes are disjoint, no doubt, but what W belongs to E means?
Each outcome of a subset.
outcomes of the subset. Okay, I know what you guys are saying. You're implying that E is an event, and we know that the event will comprise of outcomes, correct? So what we're saying is all those outcomes that are part of, that belongs to E, basically. That's what this means. So if there are 5 outcomes of this event, then this summation will sum up P of W1 plus P of W2 plus P of W3 plus P of W4 plus P of W5. 5 outcomes, right? That's what it means. All right. This is an experiment. Toss a coin until the first head pops up. Report the number of tosses. Okay. Toss a coin until the first head pops up. Report the number of tosses. Can somebody tell me, what does this sample space actually mean? 1, 2, 3. What does it mean? Why didn't I put a head, tail? I'm dealing with a coin, right?
You can get
may
ahead.
occur head all the time.
Sorry, say that again.
It may occur like head all the time, or tail all the time.
All right, but why didn't I? My question is, I toss a coin. The moment we toss a coin, our intuition always says, put a head in the sample space. But why do I see a 1, 2, 3? Why?
You can get it during the first toss. You can get it during the second toss.
That is right.
Because our outcome is not of getting head or tail. It's to find the nth time.
It is to define the, okay,
number
good point.
Of
So exactly, the outcome is not head or tail. The outcome is the number of tosses until the first head. That's how we are defining the nature of the experiment. All right. So always remember, folks, the sample space comprises of outcomes. The outcomes come from the nature of the experiment. Here, the nature of experiment is, we're not concerned about the outcome of, a single toss of a coin. The outcome that we're concerned about is the number of tosses it takes to get the first head. A question: how many elements would be there in this sample space?
Infinity.
Okay, why?
Because first time tail may be occurring, and we don't know when it may be occurring.
Sabri, you're not very audible. Am I the only one facing some trouble? Someone else. It's okay, Sabri. You got the answer right, but I want to hear some arguments.
Is it n-1?
Sorry?
Is the number of... Oh, no. No, sorry.
Yeah, there is a possibility of not getting head.
At all, correct? I can continue to get tails. So which means there's a possibility of not getting head at all, which means my sample space would look like 1, 2, 3, 4, 5, 6, all the way up to infinity. Now they've defined a probability function. Forget what the probability function is, all right? They've defined it, okay? And let us say for some reason, we are certain that this probability function for any n is of course the number of, n by the way is the number of tosses it takes before you get the first head. So let us say this is the probability function. Can somebody tell me, is it indeed a probability function? I'll give you one clue. Let us say rule number 1 is satisfied. Is rule number 2 satisfied? We know that for probability functions to work, 2 rules have to be satisfied, right? Rule number 1 and then rule number 2. Can somebody tell me if rule number 2 is satisfied for this? If this is a probability function? Anyone? I say rule number 1 is satisfied.
In the case where we get at least one head, right?
That is right. This is the probability function. I say rule number 1 is satisfied, which means P of 1, P of 2, P of 3, P of 4, P of 5, all of them are between 0 and 1. Rule number 1 is satisfied. But for some function to be a probability function, rule number 2 also has to get satisfied, correct? My question is rule number 2 satisfied here? Okay, this time I'll open it to all.
Actually, it depends upon the probability and the coin or the nature of the coin.
Nope, it doesn't.
No, it will be satisfied for everything.
Why?
Because see, the probability is always between 0 and 1, right?
That is rule
So
number
1 minus anything will be less than 1.
Correct.
To the power of that number,
that
right?
is rule number 1. That is rule number 1. How about rule number 2?
So sum of all these probabilities will be 1.
Why? I never said so. This is some function. I don't even know whether the sum of the probability will be equal to 1. I come up with a random function, Sirisha. Right? I don't know. I'm worried. I've come up with this function now. Now I want to declare to the whole world that, look, this is a probability function. I say, look, I have ensured rule number 1 is satisfied. But how do I ensure rule number 2 is satisfied?
This is sigma n equal to 1 to infinity.
Correct.
This thing, right?
Correct. Then go ahead. Continue with your argument.
This is like Taylor series or?
No, what Taylor series? Come on.
This is like some series, right?
What series? Yeah. What
Geometric.
is that? Geometric progression? Correct. It's a geometric progression. So sigma 1 minus p whole power n minus 1 p n equal to 1 to infinity. Correct so far?
Correct. Correct.
Right. Can we take p out of the summation?
Yes.
Why?
Because we are doing sigma on n number of tosses.
Exactly. So p goes out of the summation. So it is simply sigma 1 minus p whole power n minus 1.
Correct.
Correct. When you sum a number like this.
N into n plus 1 by 2, right?
Nah. That is some 1 plus 2 plus 3.
Progression. Yeah, that is arithmetic progression.
That is sum of natural numbers. So how do you figure out this?
Geometric progression, right?
Right. So how do you figure out?
Geometric progression, there will be one formula.
All right,
1
folks.
by 1 minus
R, correct? Remember?
1 by 1 minus R.
Yeah. Right.
When for that infinite series. So 1 by 1 minus 1 minus p, right? So that's p. 1 minus bracket 1 minus p.
1 minus 1 minus p.
That's p. So you have taken the p out of the sigma. The summation of the sigma is p. So p cancels, correct?
P by p1.
1. That's it. Which is why this is a probability function. Right? And we know that the summation that you talked about, 1 by 1 minus r, will work only if, what are the criteria?
R is
less than 1.
Less than 1.
Right? Less than.
Not equal to, less than 1.
The modulus is less than 1, correct? It has to lie between minus 1 and 1. Only then it will converge. Otherwise, geometric series will, what will happen to geometric series?
It will diverge.
Exactly. If the ratio between one and the next is greater than 1, then it will diverge, right? So if you start with 1, if the ratio is 2, it will go to from 1, it will go to 2, 2 will go to 4, 4 will go to 8. But if the ratio is half, from 1 you go to half, half goes to 1/4, 1/4 goes to 1/8. So which means it will converge, right? Anyways, the point is not that. The point that I'm trying to make here is this is a probability function because both rules are satisfied. Okay? Any questions so far? Okay, all right. I'm not going to get into conditioning, but I'll briefly throw a problem at you to think about. Okay? Here's the situation. Now we're going to move into the world of conditioning. It says all probability is conditional. It's a very philosophical statement when you say all probability is conditional. Because every definition of probability means it depends. So whenever you say, right, even something as trivial as, say you toss a coin. I say it's a fair coin. But then, can you think of a condition? I say it's head or tail, but it also depends on a condition. For example, you're hoping that the person who's tossing the coin is tossing it fairly. Correct? Because the coin may be fair, but you can have, you can be a very smart tosser who can ensure that you'll always get a head. So every definition of probability is conditional. That's a very philosophical statement. But let me give an example for you to think about. Here is a scenario. Ancient Tamilagam had a unique climate. When the rain gods were generous in the rest of Hindustan, which is from June to September, Tamilagam would be blazing hot. A few thunder showers were the only respite, which is from June to September. So there will be some thunder showers in Tamilagam. Okay. When the monsoon retreated in the rest of Hindustan, which is from October onwards, Tamilagam woke up to the northeast monsoon during the months of Aipasi and Kartige, which is October to November. All right. Both were equally rainy. So Aipasi and Kartige, the 2 months, October, November, is considered to be a rainy months in this case, in Tamilagam. And both are equally rainy. Both Aipasi and Kartige are considered to be rainy months, equally rainy. For the rest of the year, rains were scanty. So this is the unique climate of Tamilagam. June to September, it's hot, some thunder showers. Aipasi Kartige, which is October to November, equally rainy. The rest of the years, the rest of the year rains were scanty. I'm going to throw some probabilities. Look at the first probability. It says it rains in Tamilagam given that it's the month of Kartige. That's question number 1. It rains in Tamilagam given that it's the month of Kartige. Leave question number 2 for the time being. Let's flip to question number 3. It's the month of Kartige given that it rains in Tamilagam. Okay. Look at the first and the third. In the first one, it says it rains in Tamilagam given that it's the month of Kartige. The third one is it's the month of Kartige given it rains in Tamilagam. Now, can somebody tell me, are both probabilities the same?
No.
Sorry.
No, both are different.
Okay, why?
The first one says that it rains. Okay. And what is the probability that it is the a month of
No, be
no,
careful.
Given that it is the month of Kartigai, what is the probability that it rains?
Okay.
It always rains, right, in the month of Kartigai. That is
Correct.
first question.
All right.
The third one says that given that it rains, okay, it means that it is raining. What is the probability that it can be Kartigai?
Correct. Now, question. Intuition, according to you, which one do you think will be higher?
First one will be higher.
Why?
Because we already know that, right? It is month of Kartigai. It always rains as per the statement which is already given.
It's definitely going to happen.
Almost definite, correct? Right?
Correct.
And the second one, and the third one?
It may be Kartigai, it may not be Kartigai also.
Correct, that is right. But take a guess. Given all the statements here, what will be this probability close to?
Half.
Yes. Why?
Because it can be Pasi or Kartigai. We have only 2 months, right?
Yeah. And then there are thunder showers. So which means close to. The rest of the months, June to September, you'll get some thunder showers. So there is a possibility that it could be June, July, August, September as well. There is a possibility because I said a few thunder showers were the only respite. All right. But that probability is going to be low because, as I told, the statement was very, it was very clear that Tamilagam would be blazing hot from June to September, right? Except for those thunder showers. So you're right. Aipasi, Kartigai are the two rainy months. So which means the probability of the third, statement will be close to 0.5. And the second one, of course, there's no clear answer. But don't you see that second one is like, you'll have to look at all months from Jan to December to figure out the probability of rains in Tamilagam. Would you agree? Anyone who hasn't understood this question and the answer that Sirisha and Yash gave? All of you understood? Okay, I'll just pinpoint somebody. And I want to ask them to explain to me. Okay, Ministry. Can you explain why this probability and this probability is different? The first and the third.
In the first one, it's given that in the month of Kartigai, even as month of Kartigai, and it rains in Tamilagam, it's 100% sure.
Okay.
In Kartigai, it rains.
Okay.
So, and then in the third question, it's given that it rains in Tamilagam. It might be Kartigai or it might be Aipasi.
Correct.
So the probability is half.
Close to, because there can be thunder showers in other months too. So which means, but yes, close to half, correct? Because Kartigai rains and Aipasi rains will dominate the rainy season in Tamilagam, right? You do get rains from June to September, that will be scanty, but you do get rains. But you're right, okay? I hope all of you understood this because it's extremely important. Because the next step, I'm not going to do it today, but the next step would be to clearly define this in probabilistic terms. So we'll have a clear expression that helps us to calculate something like this. We'll come to that in the next session. But what you just saw was this basic idea that P of A given B is not equal to P of B given A. Right? Why? Anybody? I just said a statement. P of A given B is not equal to P of B given A. Why did I say that? Anybody? Take this particular context. There's an event A, there's an event B. So there is an experiment that happens and there are outcomes. You have events. There are two events that are defined on the outcomes, A and B. I'm saying P of A given B is not equal to P of B given A. Why? Define it in this context.
So here, yeah, Kartigai is dependent on rains. Like whenever it's Kartigai, it will always rain.
Okay, what is,
so it's
define
like
A, just define A and B for me here. Just can we say it rains in Tamilagam as event A? And
yeah,
it's the month of Kartigai as event B, correct? Can we do that? So don't you see that I can define the first thing as P of A given B, right?
Yeah.
And the third
so
statement
A
is sorry, go ahead.
No, you go ahead.
And the third statement, can I say it's P of B given A? Right? We can say that, right? And we clearly saw that P of A given B is not equal to P of B given A. Isn't it? We clearly saw that. We reasoned it out, with this example. So that's one of the basic axioms of conditional
condition
probability.
that A is not equal to B.
Oh, of course. That's evident. If you say it rains in Tamilagam, given it rains in Tamilagam, then of course, then it's 1, isn't it? The probability of that happening is 1, right? So, or rather, it doesn't mean, yeah, it's 1, because you're saying that if it rains in Tamilagam, then of course it's raining in Tamilagam. So probability of A given A is 1 or B given B is 1, right? Okay. So any questions so far? I'm going to stop here. I'm not going to continue, but any questions so far? All right. Actually, we wanted to do some C 4.5. It's already 12. I don't want Sandhya. Can you just briefly don't go through the details, but can you just help us, Sandhya or Kayal? You have the presentation with you, right? Just briefly tell us what is C 4.5, just how different it is from ID3, and in the next session we'll start with your bit. Where you explain to us some of the aspects of how you've implemented C 4.5, how different it is. You have some calculations as well. We'll go through that in the next session. And if time permits, I'll continue with probability in the next session. So, Sandhya and Kyle, over to you. I'll stop sharing. Just take us through what you have on C 4.5. No need to go through a lot of details, but just briefly.
Okay, we see. Shall I start presenting my screen?
Please go ahead.
Okay, this one is today I'm gonna walk you through the C 4.5 algorithm for machine learning. So let's see what is C 4.5 algorithm. So C 4.5 is an extension of the algorithm we already discussed, that is iterative dichotomizer 3 algorithm. The ID3 algorithm is also developed by Ross Quinlan, who also he finds some cons in that algorithm. So he added some attributes. He added some what is oh my god. He developed it with he developed an algorithm to overcome that cons. So that one is C 4.5 algorithm. So as we already know, it is a algorithm used for generating decision tree, specifically for classification tasks. And then we
by
are
the way,
going to see.
why is it 4.5?
Yeah, I think that is a version 2, but C stands for C program, since he coded most of the programs in C.
Okay, so
Am I
basically,
rightly
I think, okay, I don't know much. There's nothing much available on Google about why it is C 4.5, but it looks like he wrote this book, and at the end of the book there are a collection of programs, and for some reason he calls that whole package as C 4.5. That's what I could interpret. Even I couldn't really understand why he chose to call it 4.5, because we didn't go through that package. Anyways, go ahead.
Okay. Then we said there are some cons with the ID3 algorithm, right? So we are going to see what are that cons. The first one is it cannot handle continuous data. When we give continuous data to ID3 algorithm, say we have only two classes. For the tennis example, we had to class right, the player don't play and play. So in this case, if we prompt a continuous data to the tree, it will give a lot of the tree is complex. It becomes for say the humidity is 70, it will give S, and for humidity is equal to 71 also, it will give S. So, and the humidity equal to
Sorry, if you don't mind,
71.1.
Going to ID3, it's a question for you, Sandhya. ID3 algorithm.
Okay.
So you had features, you had a target variable, right? ID3, when it talks of features, what sort of features can it handle? What are the nature of the features?
Discrete features, countable.
Countable, all right. So it cannot handle. So when you say continuous data, can you give me an example?
Temperature is also a continuous data.
All right. So if ID3 has to handle temperature, how would ID3 handle it?
It will give a lot of leaf, I guess. Correct me if I'm wrong.
Or alternatively, don't you see a user should convert the continuous data into categorical, correct? A user has to do it.
Yeah.
Something like, you have the data set, you know that ID3 cannot handle it. So you would convert the temperature into, say, low, high, medium, something like that, and then give it to ID3 algorithm. That's one way to handle it, correct?
Yes, we see, but yeah, in the previous tennis example, we didn't use the numerical value of humidity.
Correct.
We just used hard, medium, and
which means somebody converted it for us, isn't it?
Yeah.
Correct. Though humidity, I think the original data set would have had numbers, I suppose.
Yeah.
Right? And then somebody would have converted. So it's some user has to convert, or a data analyst has to convert that data to, as you said, high, whatever.
Medium.
Whatever it is, right?
Okay.
And then use that in the algorithm. Okay, so that's number one. Go ahead with number 2 and number 3. Go ahead.
So I should have written something like it cannot handle numerical data, continuous numerical data.
But continuous, we understand. I think all of us understand that. Can continuous occur in the world of, say, string data? Is it possible? I don't think so. Right? So
no,
you don't.
It will not occur.
Right? So continuous is fine. I think what you've mentioned is fine.
But numerical values can occur in discrete world, right?
Okay, good point. Numerical, but not continuous, isn't it?
Yeah.
So, for example, I can group people into 3 groups, call them group 1, group 2, group 3. Of course, group 1, 2, 3 is numerical, but that doesn't mean it's continuous. So what is continuous?
Continuous is it has an order. Like if we are measuring temperature on ocean surface with a temperature sensor under our boat.
All right, and what else? It can take any value between 2 numbers, right? That's what we mean by continuous, correct? So if you have 70 and 71, it can take 70.1, 70.2, 70.3.
Infinite number of values between.
Exactly, right? Okay. Now go ahead with point 2 and point 3.
So the ID3 algorithm will not handle the unknown values. If we for the unknown value of an attribute. For humidity, if in the real world data, most of the attribute values which are handled manually will not be entered properly. If a patient is visiting a doctor, sometimes he forgot to mention the date, or sometimes he forgot to mention our name itself. So at that cases, IDT algorithm will not work. It will produce an error in that case, I guess. Am I right, Lucy?
Yeah, go ahead, please.
Yeah, and then there's something called tree pruning. If there is a subset, here there are 2 types of pruning. Pruning is nothing
but don't get into the types of pruning, but just tell us the concept of pruning. Why do we need pruning?
Reducing say a subset into a leaf. That is called a pruning. If a subset has 2 different classes, say play and don't play, and the subset is mostly populated by the don't play class, then we can replace the subset with a leaf with some error, and the don't play as a final class.
Why do we need pruning?
To reduce the complexity of the tree, I would say.
What if you don't reduce the complexity? Go back to that example. You remember? What does ID3 do? Remember the pitfall of ID3 algorithm? The most fundamental pitfall of ID3 algorithm?
Information gain.
That is right. What is the pitfall there? Anyone?
Entropy of the parent.
Very fundamental issue with ID3. We did discuss this in the sessions.
If you add one more training case, then the tree will be like completely changed. It will be.
Okay, that's one way. Another way. What does ID3 algorithm encourage? If I have an attribute,
to exactly figure out.
No, let's say I have an attribute. Let me pose this question. I have an attribute that can take 15 different values, unique values. I have another attribute that can take only 2 values. Which one would ID3 encourage?
15 values.
15 different values.
Why?
Because it has more
high
entropy, right? High information gain.
After splitting, the entropy will become less, correct?
Yeah, and more information gain.
Exactly, right? So ID3 encourages a lot of splitting because that's one. And you remember, folks, which means if you recollect what we discussed in one of those sessions, we said it will keep going down the tree until you get to a stage where
you get yes or no.
Exactly. Until, of course, there'll be situations where it can't get to that stage, but ID3 attempts to get to a stage where it traverses down the tree and finally at one stage you get all yes or all no. It stops. Now, what is the problem with that?
Overfitting.
Exactly. What do you mean by overfitting, Kyle?
It's not generals.
Okay, again, I asked Kyle. Let Kyle answer. What is overfitting here? What do we mean by overfitting?
Work. It exactly fits the training data and it could not figure out the real world problems. It could not work well with the real world problem.
Okay, so to be more precise, it exactly fits the training data. So it constructed a big tree. What will be the problem when I use this decision tree on, say, the validation set?
In validation set, it might be facing some combination that it has never met.
All right.
So at that time, it can produce some wrong output.
All right. Okay. Excuse me. So Kyle is right. When you use ID3 algorithm and it goes all the way down, what it does is it tends to overfit the data, which means it will fail to generalize. Now, again, these are terms that everybody should have known by this time. What does generalization mean? Anyone? I mean, just give me an answer in English. I'm not asking for a mathematical expression. We never do math. I mean, we never came up with a mathematical expression for generalization, but what does generalize mean?
Here also we deal with generalization.
Sorry, say that again, Sandhya. I didn't understand.
Yeah, here also we are dealing with generalization where in the case we have say we have 168 cases. So there is only one don't play negative cases there and all other cases are remaining cases are positive. So what the ID3 algorithm will do is it will split the tree again and again until the don't the negative one is classified. So we can generalize the when we are testing the model against a validation set, it will sometimes this condition is also called as overfit. Am I wrong?
Correct.
Am I right?
You're right. Overfitting. So what does generalization means? That's the question.
So it in C 4.5 it will not do something similar to ID3. It will generalize the whole subset to a positive case, which is mostly
I agree. Okay, let me put it this way. One model that overfits, another model that generalizes. Okay? Two models. ID3 overfits, C 4.5 generalizes. All right?
Yeah.
You have test set, you have validation set. Tell me what can potentially happen when you use ID3 as against what can potentially happen when you use C 4.5. So what will happen when you use ID3 on the test set? What would happen? And what would happen when you run ID3 on the validation set? And explain the same thing as to what would happen if you do the same thing with C 4.5 algorithm. I mean, the model. Go ahead.
We are testing the validation set against the ID3 algorithm. Here, for a lesser amount of negative cases, we are traversing the tree. So
this is ID3, is it, or?
Yeah, ID3.
Okay, go ahead.
First, I should. Okay. And then what happens is for there are and say in the validation set there are so many negative cases. What in this case the ID3 algorithm will, because there is only one or two positive negative cases in the subtree which is populated by the negative positive cases, it will check for that. It will traverse.
No, we don't need the details to that extent, Sandhya. The question is, what do you think will happen? In general, you take the ID3 algorithm.
Okay,
you have test set and validation. Yeah, go ahead.
Generalize, it will not perform well on the validation set.
Exactly. And with C4, okay, it will do very well. It will do very well on the training set. Would you agree? I'm talking of ID3.
Yeah.
Right? C 4.5, would it do better than ID3 on the training set? What is your gut feel?
No, it might be better or might not be better.
Might not be. All right.
Yeah.
But then is it expected to do much better on the validation set?
Yeah, it will do much better on the validation set.
All right. Why? Because it generalizes.
Yeah.
Right? Okay. Abhinav, you wanted to pitch in.
Yeah, actually, that's what I was trying to say for a long time. In training data, where in case C3, in CD3, it would have high accuracy, whereas in validation, it would fail. But in C4.5, it would be scoring well in training as well as validation. So
again, training depends. It'll do reasonably well. Maybe not as well as ID3, right? Because the number of branches,
Actually,
the number of
ID3,
the depth could be less.
If I'm not wrong, for each example, it would result in a branch.
Potentially,
so that's
could happen. Could happen,
fails.
right?
Yeah.
Okay.
Yeah.
Question again. General question. Why is it important that a model has to work really well in the validation set? Let's say I have a model which does extremely well in the training set and does poorly in the validations. What's wrong with that?
It will not perform on the general cases, unseen cases.
All right. Okay, that's right. Okay, well done.
It would have memorized if it not.
Exactly. So what is that called? What is that term in machine learning world? When an algorithm memorizes, what is it called? Overfitting or rote learning? Both are same, right? Like how we mug up. It's like how we solve, how we prepare for exams. If the questions are from the book, exactly from the book, we do really well. The moment you give a question out of syllabus, we fail, right? So our training, our examination training is a good example where we are trained
on.
Exactly, it's not adaptive. So even the way we learn stuff isn't generalized. It's very specific to that book and maybe the notes that your ma'am has given or your sir has given. So your entire mind is trained on that. And the moment somebody gives a question that goes beyond what is there in the notes, we all scream out of syllabus, right? The world of machine learning model building is not any different. Okay. I think let's stop here. It's already 12:15. We'll continue with this in the next session. Any questions so far from the audience?
VC, I have one doubt. Actually, today is my first session. I didn't study about this ID3 and C4.5.
Okay.
I have studied random forest. It sounds similar. This ID3 sounds similar to the random forest. But what is the difference between the random forest and this ID3?
Okay, good point. To be very honest, I don't know yet. Okay.
Okay.
Why? Because I haven't learned random forest yet. Kirtana, sorry. Let me make it clear here. So all of us are learners in this group, by the way. So it's not as if there are experts sitting here. If Bhargav joins, Naveen joins, they are the experts. But otherwise, all of us are learning. Hey, hi, Bhargav.
The entire meeting. Hello.
Sorry, I didn't see your face. All right.
So
they are the experts, by the way. I'm not. So we will do random forest. Certainly, we'll do it. And once we get there, we understand that algorithm. We'll certainly handle this question.
So yeah, but it's all tied. I mean, maybe use this time to learn a bit more. It's like VC alluded to it towards the end, talking about overfitting and generalization. This is a challenge that any algorithm in decision tree has. Right? We'll see a few different algorithms.
Yeah.
They all have the same kind of problem.
Yes.
So there have been a lot of approaches to how to solve this, right? Interesting trivia is that random forest came in 1991 or 1992. It's not like it's already 32 years old algorithm that came because of the challenges of having overfitting being a challenge in decision trees, but it's built using decision trees. We'll cover in detail. So there are two ways in which we can do. One way to think about is, can I build my model sequentially or can I build my model parallel, right? So two approaches to doing it. And that's given rise to the concept of random forest. It's another thing that you'll also keep hearing, gradient boosting algorithms. So they're all built on tree-based algorithms. This is the start of tree-based algorithms. We saw a few linear models, linear regression, logistic regressions, which are all based on linear lines, which is also why we learned linear algebra. This is another paradigm of building models, which is all tree-based models, which are partitioning algorithms. So we take data and we partition them into spaces, create bins, and then put them into it. Please go watch the previous videos to get a sense on where these things are. You have a lot of catching up to do, but when you do it...
But she has a background. Kirtana, why don't you introduce yourself to this audience?
Yeah, sure. Actually, myself, Kirtana, already VC mentioned about my name. And then now I'm doing my MSc Data Science. I'm a final year student. I'm doing MSc Data Science in Christ University.
And anything else?
Wow. In Christ in Bangalore?
Yes.
Oh, nice. Okay.
So she happens to be a cousin of Rakesh. Is that right? You're a cousin of Rakesh, right?
Yes.
All right. So I've known her for a while. So she was interested in joining. So I said, why not?
Hey, welcome. Welcome.
She has some catching up to do. But
asked me a question about ID3 and C4.5. I didn't even have an idea about it. But now they were talking about this algorithm. It sounds similar to the decision tree and random forest. And then I searched for it. That's why I came with this question, because it's not same. Because decision tree is like a tree structure, but this is the hierarchical structure. So I just wanted to know.
All right.
Understood. Got it.
Bhargav, any closing comments?
No, nothing from me. This is good.
I have something to mention. Like,
Yes,
it's,
but
yeah, it's always great to learn something with diverse group of people, right? Like when I see like bunch of folks from third year, final year, and when I see Sri Shaka, then I can't find any difference. And I am now feeling like I am sitting with a student who is doing MS in data science, and I am learning along with her. It's a great privilege. Thanks for creating the space, and I hope in future whatever you learn, you try to create something like this, and we all will join whatever it is, cooking or whatever you're doing. I always try to join. Thank you so much.
Pleasure. Thanks to Bhargav.
Thank you.
Okay, then. We'll stop for the day. We'll continue on Friday.
Awesome. What's the agenda for Friday? What will we cover?
She's going to continue. Sandhya and Kyle, they're going to continue with the C 4.5. She just touched upon the deficiencies in ID3 and how it is addressed in C 4.5. So they've written a bunch of codes as well. They're going to explain how those deficiencies are handled in C 4.5. And if time permits, I'll continue with conditional probability. That's the agenda for Friday. All right.
It's good. Okay.
Okay. Cheers.
Thanks, everyone.
Bye.
Bye. Bye.